I will try.
Okay. Everybody to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Professor Sigiswald Barbier from the Ghent University in Belgium. The title of his talk is Diagram Categories of Brauer Type. Please.
Okay, so thank you, and also thank you for inviting me to present my work here. So the goal of this talk is to convince you that a diagrammatic approach to algebras can be useful. So most of my talk will be about associative algebras, but since it's a non-associative seminar, I decided to give a motivational example, which I will not explain actually in this talk, and this talk is not about, but it gives some idea why we want to use diagrams. So a famous conjecture, so in the end of the 70s, was by Kardemans and Lustig. For algebraic groups in characteristic 0, they conjectured how we can expect to express the characters of the simple modules in terms of Kardemans and Lustig polynomials and the known characters of standard modules. And this conjecture was quite soon afterwards solved. But Lustig also made a generalization of this conjecture in positive characteristic. And this conjecture took a lot longer to establish. So I think in the 90s, some people were able to show that it's actually true for very large P. But then surprisingly, almost 10 years ago, Williamson showed that it's false in general. So, and that was quite a surprise for many people in the field that this conjecture does not hold. So, and the way that Jordy Williamson proved a counterexample in this paper on Schubert calculus and torsion explosion, he uses this diagram we see on the left. This gives a counterexample. I will not explain how he comes to this diagram because I'm really not an expert on this topic. But it is, I think, perhaps the most famous or the best example of how diagrams can be used to solve problems that were not able to be solved before. So if you want to know more about this approach to diagrams and this thing, I can recommend this book by Williamson and a lot of other co-authors, Introduction to Circle Bimodules, where they explain this graphical calculus. But in this talk, I will actually focus on a more basic, simpler example of diagram algebras, which I will in the end also show some applications to Lie theory. So a basic question in algebra and group theory is how can we look at a group? How can we define a group? And there are different approaches. So we can start by describing a group abstractly. So for example, we can describe the permutation groups by saying that the elements of Sn are just permutations of an object. And then multiplication in this group is just composition of the permutations. This is a very nice definition. It's also clear what the permutation group then is. One disadvantage of this abstract definition of a group, just saying what it is that it's hard to calculate with it because we don't know how we can, we have no formulas at the moment, so it's hard to calculate with it. So, so another way to describe a group is just give all elements explicitly. So for example, if we have the permutation group of 3 elements on 3 objects, then we know that one permutation is the identity. We have the permutation that switched 1 and 2, permutations that switch 2 and 3, permutation that switch 1 and 3. We have a permutation that maps 1 to 2, 2 to 3, and then 3 again to 1. And then we have another permutation 1 to 3, 3 to 2, and 2 to 1. So this is all the permutations on 3 objects. And now if you use this definition of a permutation group, then you also still have to specify what multiplication is, which you can do it explicitly in terms of these elements. Then it's immediately clear how big the group is. So we have 6 elements, and we can use formulas with this definition. A disadvantage of such an approach is that for S3, I can still write everything explicitly down, but it's very soon, the group becomes big, it's very hard to write everything explicitly down. Of course, you have some ways between these two approaches. So for example, you can look at the matrix group of orthogonal matrices. Then you can define it abstractly just as a group of all matrices, but you can also give a formula for when matrix is orthogonal, and then you can also do calculations with it. But in this talk, I will use another approach, and that's the one using generators and relations. So we just specify some generators that will generate our whole group. So for example, for Sn, we know that it can be generated by so-called Si, which corresponds to a permutation of the element I and I plus 1. If we then let I go from 1 to n minus 1, then we know that all permutations can be written as a combination of these generators, and these generators satisfy some relations. So we know that the square of such a generator should be the identity. We know that they commute if at least I and j are not close to each other. So if I and j, absolute value of I minus j is bigger than 1, then they commute. And if they're next to each other, so neighboring generators should satisfy the Brauer relation. So Si plus 1, Si is equal to Si plus 1, Si plus 1. So that's another way to define, in this case, a group, or we can also define algebras in this way, is just choosing generators and relations that these generators should satisfy. So this mostly leads to very compact ways to present algebras or to present groups. One disadvantage of this approach is that it's not immediately clear if we give, so this representation using generators and relations is highly non-unique. So you can give different generators, different relations, which could give the same group. And it's a non-trivial problem to determine if or when two presentations give actually rise to the same algebra. So another disadvantage of this approach is that it's not immediately clear if I just give you a set of generators and a set of relations. Do they actually define, is it a well-defined algebra? How does this algebra look in general? So the example that in this talk will be the most important is the Brauer algebra, which I have given here a definition, I've copied from a paper, of using generator and relations. So we have, on the one hand, we have generators Si, and these Si correspond to the generators of the group, a symmetric group or the permutation group. So they satisfy the same conditions. So square to 1, they commute if they far from each other, and they satisfy this Brauer relation. But more, we also have some other generators which also satisfy some relations. So they are some kind of idempotents. And you also have some relations between those EIs and SIs. But the disadvantage of such a presentation is that if you've never seen this algebra before, it's very hard to get some feeling about what do these relations actually mean. So my goal today is to give a diagrammatical approach or diagrammatical realization of this algebra, which gives the same realization using diagrams. And then I want to persuade you that this gives actually a better feeling of what is this algebra and what does this relations actually mean. So another thing about these relations is that it's easily to get mistakes and that are not easily so to spot. So I said that I copied this a definition from a paper. That's actually true, but actually it contains a mistake. And if you've never seen this algebra before, it's very, very hard to see where actually is the typo in this definition. So actually the correct version of the Brauer algebra should be this one. And you probably haven't seen it, but the mistake was that these two were switched around, which even if you know the definition of a Brauer algebra, it's not so easy to spot where the mistake is. And I hope to convince you that if you use the diagrammatic parts of these relations, then if you made such a mistake, you would be immediately obvious. So how can we represent such a algebra using diagrams? So I will start by first again introducing the symmetric group algebra as diagrams, since we have seen that the Brauer algebra contains this symmetric group algebra. And this way of representing the symmetric group algebra is perhaps some way that you already know. So what we'll do is we'll take some nodes or some dots or some points. We take n northern nodes or n top nodes, and then we also add n southern nodes or n bottom nodes. What we'll then do is we'll connect these nodes with propagating lines. And if we do that, then this gives us a diagram. This is what we call a diagram. And such a diagram represents actually a permutation. So because we can enumerate these nodes. So we could say 1, 2, 3, 4, 5, 6. And then we can follow the lines to see which permutation it represents. So the 1 gets mapped to the 3. So it's a permutation that maps 1 to 3. 2 gets mapped to 4. 3 gets mapped to 1. 4 to 2. 5 to 6. And 6 to 5. So we indeed see that such a diagram of certain nodes and propagating line between the nodes represent a permutation. And if we want to multiply two different permutations, what we will do is we take our two diagrams and put one diagram on top of the other. And then we connect the lines. So we see that we started here from permutation 1, from the object 1, first gets mapped to 2, then we'll look what happens to 2, and 2 gets mapped to 4. So we see in the end, we'll get permutation will map 1 to 4. So we have to connect all those lines, and then we get a new permutation, which is indeed the composition of the two previous permutations. So in this way, we have defined diagrams, and we have defined the multiplication of these diagrams, which gives us then a semigroup, or in this case, a group. We then want to get an algebra out of it. So, for example, the symmetric group algebra, what we then just do is take formal linear combinations of such diagrams. So how do we then get to the Brauer algebra? We take the same approach. So we take again nodes, let's say S northern nodes and R southern nodes. So, but now we don't assume that the amount of nodes, the top and bottom nodes are the same, because we not only use propagating lines, but we also use cups and caps. So cups are lines that connect to northern nodes, and caps are lines that connect to southern nodes. So this gives a rise to a new kind of diagram. So we not only have propagating lines, we also have cups and capses, which in particular indeed means that we don't really need to have the same amount of nodes on the top and on the bottom. How do we then multiply Brauer diagrams? Just in the same way as for the symmetric group. So yes, just to remind you, if you just have propagating lines, then we indeed get the symmetric group as a sub case of the Brauer algebra. So, but how do we multiply Brauer diagrams? Just as for the symmetric group, we first, of course, we want compatibility. So we want that the amount of southern nodes of the first diagram is the same as the amount of northern nodes of the second diagram, so that we can put first diagram on top of the second diagram. And then again, we just connect lines. So we'll connect those lines. And then we will get a new diagram. But you see here that now something new can turn up that we didn't have before. We can have closed loops. And in our definition of a Brauer diagram, there are no closed loops. So we should somehow get rid of this closed loop, and we will replace each closed loop we encounter with a parameter delta. So just for each closed loop, we add a parameter which is contained in our field. And that way, we after multiplying, get again a Brauer diagram, perhaps multiplied by some factors. But since we are interested in an algebra, in the end, we'll take finite linear combinations. So this factor doesn't really bother us. So, and then my claim is that if we look at these, so we have defined a Brauer algebra, we can define as consisting of Brauer, so the Brauer algebra and delta, consist of diagrams, of Brauer diagrams with n northern knots and n southern knots. We have a well-defined multiplication, and my claim is that this is the same algebra as the one we defined before with generators and relations. So what we do is this as E generator, we map to this diagram, which indeed corresponds to a permutation of I and I plus 1. Then we have these EI generators, and that these we map to such a cupcap diagram, where again we connect the I with I plus 1 southern node and the I plus 1 northern node. And then the relations we had before, if we express them using diagrams, we can easily see that is indeed what we expected. So the first relation we have here says that indeed the square of this Si is the identity. Here we had this fact that the square of this EI is some kind of pseudo-idempotent. So we get the same diagram again, but with the delta, because indeed we have here this, we look at the square of EI, we get here closed loop, which we replace with this delta. Then we have the other relations we had before. So we had these EI as I just gives us EI the same as I EI. So we see that if we twist a cup or a cap, we can just untwist them, because if you then also the other relations we can easily see in this diagram. So we had that this commuting relations between diagrams. These are for the SI, but we have the same for the EI. They also commute, and also the mixed terms commute. What we have here is this braid relation, maybe perhaps you're familiar with. So, and we immediately also see a disadvantage of using diagrams is that it takes up a lot more space. So the relations in formulas, you can just write down on one slide, but if you write them out in diagrams, we see that we immediately have a lot more space to take. So you will get as the EI is EI plus 1 EI. So that was the relation what was actually contained a mistake. So they switched around these two. So these two were switched around, but in diagram form, it's immediately clear that it indeed should be EI plus 1 is EI plus 1, EI plus 1, because it's actually just a kind of straightening relation we have in our diagrams. And then we also have some final relations, which mixes SI with EI plus 1. It's kind of actually kind of sliding relation that if you you can bring this line to the other side, but then of course we have to add some straightening so that we get that it's SI plus 1, EI plus 1, and here we have the opposite relation. So actually we have not done really anything then in the presentation just doing generator relations. We just have replaced our generators with diagrams, and then we have given these relations we had before, we interpreted in diagrams, but then it's a lot more easier, at least to me, or it gives a lot better feeling of how these diagrams actually behave and what kind of relations we should expect. And it also gives a better feel of if you should we add relations or if you forgot the relation, it's much more clear in the diagram approach. So another advantage I find of these diagrams is that it's easier to come up with proofs or to follow proofs, and also to come up with examples, because you have to simplify relations using formulas. I find it a lot harder to do it than just simplifying the same using these diagrams, because in these diagrams it gives it gave the feeling much more natural to me. But we could see that actually we have still here a lot of relations, and some of these relations, so as these commutation relations, you feel that they could still be simplified, which is true. So I will show later how we can, using a categorical framework, how we can simplify these things. But before that, I will do a slight intermezzo to kind of motivate why are we interested in the Brauer diagrams. So myself, I come from originally from representation theory of Lie superalgebras, and I started to get interested in these diagram algebras, especially since you can use these diagram algebras to also get some information on Lie superalgebras. And the way to do this is so-called Schur-Weil duality. So in representation theory, we know that if we have a vector space V, then we can act on it with the general linear group. We can act on V. We can act on V, then we can also just act on the tensor products of V, just by diagonal action. But once we have tensor products, then we also know that we can act on it with permutation group just by permuting the factors of our tensor product. So we can permute factors of our tensor product. We also have an action of our general linear group on this vector space V. And the nice thing about these two actions is that they actually commute. So these two actions commute, and we have even more, they are each other centralizers. That is actually what Schur-Weil duality says, that the action of the general linear group and the action of symmetric group algebra are each other centralizers, and we can use this Schur-Weil duality. So if we have information on representation theory of the general linear group, we can use that to transform on the information of the symmetric group, or the other way around. So the Schur-Weil duality can be used to link representation theory of these two groups to each other. And the Schur-Weil duality has been generalized in many more settings. So we started with a general linear group, but we know that, for example, the orthogonal group is contained in the general linear group. So the orthogonal group will still act on this tensor product of V. And then we can also look at what is the centralizer. And then since symmetric, the orthogonal group is a subgroup of the symmetric of the general linear group, the centralizer should contain the symmetric group. Since if we get smaller on the left-hand side, the centralizer should get bigger on the right-hand side. And what we will get here is exactly the Brauer algebra. Brauer algebra with parameter delta, in this case, will be the dimension of V. So, but the surprising thing is we can not only look at the orthogonal group, we can also look at the symplectic group, which is also a subgroup of GLV. And then we will again get the Brauer algebra, but now with our parameter delta. Remember, that was parameter we get by replacing closed loops, will be now minus the dimension of V. And this looks perhaps a bit strange in the beginning, but there's actually some deeper lying reason behind this. And the fact that we can not only do this for the general linear group, but we can also do it for a super case. So we can have V a super vector space, and then we can, in super case, it's mostly more easier to work with on the algebra level, but doesn't really matter that much. So we can act with a general linear superalgebra on this vector space V, which is now a super vector space. So super dimension of V should be Mn. So it has an even part of dimension M and an odd part of dimension N. And then we can still act on powers, but since I've used here the notation N, should perhaps now use, say, R. And then you can still show that symmetric group algebra still act on this powers, and this will still be sort of centralizers, but then you can now look at the orthosymplectic Lie superalgebra, in which case N should be even as a subspace. And then the surprising thing is that on the right-hand side, the centralized algebra is still the Brauer algebra. Now with parameter delta equal to the super dimension, this M minus N, or this N should always be even. So then, as two special cases, we get a orthogonal Lie algebra and symplectic Lie algebra just by putting N equal to 0 or M equal to 0. Then this also explains why we get a minus sign for the symplectic case. Now, this general linear superalgebra also has other subalgebras. So we could, for example, look at the queer Lie superalgebra or the paraplectic Lie superalgebra. Then we again get algebras which you can also realize as diagrammatic algebras. And the surprising thing is that we'll look later also a bit like the paraplectic Brauer algebra, that is almost completely the same as the Brauer algebra. There are also other generalizations of Schur-Weyl duality. We can not only look at the super case, but you can also look at the quantum case. So you can look at deformations of this Lie groups or Lie algebras. Then on the right-hand side, or the centralized algebras will also be deformations of the original algebras. So the Iwaru-Heik algebra is a deformation of symmetric group algebra. The Biermann-Wenzel-Murakami algebra will be a deformation of Brauer algebra. Then we also have deformations of these other algebras. So these are kind of the reason why I became interested in these diagram algebras, because if we understand these diagram algebras very well, we can use it also to get information on this quantum groups or on this Lie algebras or Lie superalgebras. So for example, this paraplectic Brauer algebra, which was, remember, this is the Schur-Weyl duality of the paraplectic Lie superalgebra, is also such a centralized algebra. And the surprising thing is, although the paraplectic Lie superalgebra and the orthogonal orthosymplectic Lie superalgebra, they are not really the same, is that if you just look at the centralizers, that the paraplectic Brauer algebra and the Brauer algebra looks very much the same. So you can use just exactly the same diagrams. And also multiplication is almost exactly the same up to a minus sign. So the only difference we will have is that sometimes we have to add some minus sign in the paraplectic case, which can be calculated using concrete rules. Another thing that I maybe should mention is that the parameter delta should always be 0 in the paraplectic case. This comes from the fact that paraplectic Lie superalgebra, which mostly is denoted by Pn, is actually a sub-algebra of the general linear superalgebra where the even and the odd part have the same dimension. So in particular, the super dimension of phi in this case should be always 0, since this equal to the even part minus the odd part, which should be always equal. So the super dimension should always be 0. And recall that this was actually parameter delta. So in the paraplectic case, the parameter delta should always be 0. So another example of such a diagram algebra is the Biermann-Wenzel-Murakami algebra, which was a deformation of the Brauer algebra, which corresponds to the quantum orthogonal or quantum symplectic case. We again can give a definition using generators and relations. So this is again a definition I copied from a paper. But we will see that again. So I can give you this definition. But it doesn't say that much, at least to me. If you just look at these formulas, it's hard to get a feeling about it. But if you try to give them in diagrams, at least for me, it's much more clear what's going on. So again, I copied this from a paper, but I think it again contains a mistake. So we should add these relations, though it's not always easy to see. If you have a realization using generators and relations, if you have to add extra relations or that they actually follow from the other relations. But I think in this case, we really need these two extra relations, which has to do with this commuting if I and j are far apart from each other. So, but let's take a look at how does that look on the diagram side. So the only thing we actually do is we replaced, or SI we had replaced with this GI. And what we do is we make now a difference between the SI where correspond to crossings. We now make a difference between overcrossing and an undercrossing. So and then we still ask that if we take an overcrossing and an undercrossing, that should be the identity. So then we got similar relations as before. But for example, for this untwisting, we also add the parameter v. So this is also something new that we now have. So if we have a twist, which is an overcrossing, then we add the parameter v. And then the other relations, they're just the same as we had before. These are these commuting relations. If they're far from each other, then actually it doesn't matter in which order you do them. And we also still have the braid relation for the overcrossing. Relations using these cups and caps, they just stay the same because we didn't change anything. And then the extra relation we get is that we get some relation between the overcrossing and the undercrossing, which contains the identity and some cups and caps. And this relation is also slightly different from before, but you can, just what this relation expresses, that if we have a cup, then we can pull it over or pull it under a line. And these is can also is a bit different than the relation you had before, but it's also can deform the relations of the Brauer algebra to also be of this kind. So, but what is immediately clear from this relations using this diagram is that if we put z equal to 0, then we see that the overcrossing and undercrossing, they actually become the same. So then we get again the crossing, and then if you now put this v that we added for this twist equal to 1, then we see that we recover the Brauer diagram again, a Brauer algebra again. So if you put in this BMW algebra z equal to 0 and v equal to 1, we see that we recover the Brauer algebra, and this Berman-Wenzel-Murakami algebra are indeed true deformation of original Brauer algebra. So what have we done so far? So my goal of this talk is to convince you that diagrams can be useful. And what we've seen so far is that we have this Brauer algebra, which was related to the orthogonal or the symplectic Lie group using Schur-Weyl duality. And we also see some variants on this Brauer algebra. So we have seen deformation, it's a paraplectic case. And we have seen that we can, so first I had defined this Brauer algebra using generalized relations. We've seen that we can do it using diagrams, but at the moment we haven't really seen anything new. So the only advantage of these diagrams is that it gives a better, at least for me, it gives more feeling on how this relations acts. But another advantage of this diagram approach is that it immediately suggests generalizations. Since I actually have defined Brauer diagrams not only for the same amount of northern and southern knots, but also for different amount of knots. And this actually allows us to define a category with them. So for the language that we will use for that is so-called monoidal categories. So first of all, let me say that there's also kind of graphical calculus for categories. So if you have a homomorphism in categories, what we can do is we can graphically represent it using as follows. So we represent a morphism f from object x to y using such a kind of diagram, and mostly we just forget the x and the y and we just notate it like this. So we have our f, which we denote in this way, and then if we have composition of diagrams, composition of morphisms, we just notate it this way. Okay, and if we have an ordinary category, okay, we can say this, we not do that much, and it doesn't, okay, so we can do this, but what's the point of this? But if we work in monoidal categories, then this becomes much more convenient. So what's a monoidal category? It's a category in which we sort of have a tensor product. So we can tensor objects and morphisms in our category. So I will always working with strict monoidal categories, which means that the properties this functor should have are actually equalities. So we should have a unit object which actually behaves like a unit, and this tensor product should be associative. If you're not working with a strict monoidal category, but just an ordinary monoidal category, then these are not equalities, but these are isomorphisms, and then you should specify this isomorphism, you get associators, which makes notational wise everything becomes much more complicated. And since we only need strict monoidal categories in our case, we stick with these case. There's also actually a theorem which says that every monoidal category is actually equivalent to a strict monoidal category. So we don't really lose anything with assuming that we indeed have identities here. So once we have a monoidal category, we have such a tensor product, then we also can look at a tensor product of morphisms, and these we will graphically represent putting these morphisms just next to each other. Then what we will kind of see arising here is kind of diagrams, and we'll see that indeed it will be possible to have a category, a strict monoidal category, in which the Brauer diagrams correspond to actually morphisms. But what's important for this monoidal category is that we have so-called interchange law, which says how this tensor product interacts with the composition. And diagrammatically, we can represent it as follows. You can say that F, and here, just you should see this line also as the identity morphism. So what he actually says that F tensor 1 composed with N tensor G is the same as 1 tensor G composed with F tensor 1. So we can see that in monoidal categories, we can move these F and G up and down, and that should be familiar from these relations we also had in the Brauer algebras, where we had these commutation relations if I and J were far away from each other. And indeed, we can define a Brauer category where we have as objects, we just take the natural numbers, and these objects you should think of as corresponding to a certain, so for example, the object 4, you should visualize using 4 dots. And then the homomorphism from R to S is just a set of RS Brauer diagrams. So with R southern nodes and S northern nodes. And then you can define composition of homomorphisms just by multiplication of Brauer diagrams. So this gives a well-defined category. But the nice thing about this category is that we also have a horizontal multiplication, or we have a kind of tensor product, which on objects is just ordinary addition. And on diagrams is just given by putting one diagram next to each other. So for example, if we have the following diagram, and we want to tensor it, for example, this diagram. So we have here a diagram going from 3 to 5. Here we have a diagram going from 2 to 2. This should give on the objects a diagram from 5 to 7. And on the diagrams, it's just given by putting the one diagram next to the other. So we get this diagram. So this horizontal multiplication doesn't seem to do much, but has the advantage that now we can have a very compact way to represent this Brauer category. Namely, it's a symmetric monoidal category, so symmetric part is not that important here. But it's generated by it's monoidally generated just by one object. So you see this as a dot, and we have only 3 generating morphisms. We have this crossing, we have a cap, and we have a cup. And these 3 morphisms, together with a composition and with a tensor product, allows us to generate all Brauer diagrams. So for example, we can compose this cup with this cap, and then we can tensor, for example, with this crossing, and then we can tensor again with identity. So we have 3 generating morphisms, but we assume also that it's monoidally generated, which means that for every object we should also have the identity, or it suffices to add the identity morphism. From the object 1 to 1. And we can see that indeed every Brauer diagram just consists of composing these morphisms and tensoring these morphisms together. Then we have some relations, of course. To simplify these diagrams again, we can show that actually these relations suffice to reduce all the diagrams. So we have this braid relation here. We have kind of straightening relation. We have this sliding, so we can slide a line to the other side, and then we have this untwisting. and this loop relation. So this gives a very compact realization of this Brauer category. And we can also do this for other categories. For example, this BMW category is also monoidal category, which we have one generating object, has three generating morphisms, which you can see as the same, but now, of course, we make a difference between the overcrossing. And then the relations, they are almost the same as for the Brauer category, which is in this definition very clear. So the only difference we have is we added this parameter v for the untwisting, and we had this relations between the overcrossing and the undercrossing. So that's the only difference between the BMW category and the Brauer category. Now, of course, the question one could ask is, are there other categories of this type? So what I've told, until now, what I've told is actually all work of other people, but what I'm working on, so my research, is actually looking at categories. So what I want to do is we'll start with categories which are monoidally generated just using three objects. So these three generating morphisms. Then the question is, what kind of relations are possible? So what kind of relations can we have so that we get a nice category? And with a nice category, I mean a category for which the morphisms can be represented also using Brauer diagrams. So if you don't impose any relations, category, of course, becomes way too big. So we look at what kind of relations can you impose that gives us interesting categories, which sounds like a very broad question, but the surprising thing is that we actually only got a very small amount of categories. So we can divide them in 8 types of categories, which of course contains the Brauer category, this BMW category, but also the paraplectic Brauer category, and also Z formation, the Q paraplectic Brauer category. And then some other categories can also pop up. But the surprising thing is that it's only a very finite list. Okay, but to end my talk, I will give some applications, because until now you could say, okay, we have this Brauer algebra, and it's very nice that you can represent it using diagrams. It's also very nice that you then can make a category out of it. But do we actually gain something by having this category, or do we have just put all the Brauer diagrams together and made a big category, but can we gain information out of it? And that's actually true. We actually have gained something by constructing this category. And the reason why we have this is because, of course, so the Brauer diagram, the Brauer category contains all the Brauer algebras. So remember, this Brauer algebra is contained in this category as the homomorphisms from R to R, because these are the Brauer diagrams from R to R. But actually we have some more, because we also have homomorphisms from R to S. These do not correspond to a Brauer algebra, and this gives us some more information. So it's also the reason that the Brauer category is interesting, but we could do the same for the symmetric group algebra. So we can also define a symmetric group category in some kind of way. But then in that case, the homomorphisms that are not non-trivial are only the homomorphism between when, so the homomorphism R and S are 0 if R is different from S, since we only have propagating lines. So the number of northern dots and southern dots should always be the same. So for symmetric group algebra, you can do this, but this doesn't give you extra information. For the Brauer algebra, this will give you some extra information. And the way to do it is actually using category theory to then obtain information. So we first have to do some technicalities, because the problem with this Brauer category is it's a very nice monoidal category, but it's not abelian, it's not even additive. So to solve that problem, what we do is we take the so-called Carubian envelope of the Brauer category. So what we do is we take first the additive closure. So what this means is we just formally add direct sums. Then we also want to have direct summands. And to do that, what we do is we take the idempotent completion. So that's what's idempotent completion. So that's gives us in the anti-Caribbean envelope of the Brauer. The Brauer category, and this gives us a new category which is called the delinear category. It was first studied by Deligne in the beginning of the 2000s. And he proved that this delinear category, which you can philosophically just say it's just the same as the Brauer category, satisfies some universal property. Namely, if we have another category, which is a monoidal category, which is also symmetric and rigid. Rigid just means that we have dual, that every object has a dual object. Symmetric means that we have some kind of map, sigma, which maps every tensor product xy to yx, and this should be isomorphic. So we should have some kind of symmetry. So if you have such a symmetric rigid monoidal category, then we actually have a bijection between self-dual objects in this category of dimension delta, where this dimension should be interpreted as the categorical dimension, and functors from our delinear category to this category C. So this functor should be symmetric, additive, and monoidal. So what we do is we have this one generating object, and this we will map to this self-dual object X. And we can show, or linear has shown, that there is actually a bijection between this functors and this self-dual objects of dimension delta in our category C. How can we use this property? We can actually use this for connecting our the linear category to the representations of OSP, or if you don't know, so the orthosymplectically supergroup. You don't know what it is, just think the orthogonal group or the symplectic group, because they are contained in this case. So if you have this orthogonal group, we can look at the representations, and we have V, the natural representations. We assume that the superdimension, which is dimension of V, is delta. And then we will have the linear universal property says that we have a map which maps this generating object to this V. And then we can study this tensor, this functor. And then, for example, Lehrer and Zhang have shown that this functor is actually full. So Lehrer and Zhang actually a lot of papers on this topic. So I mentioned here this paper on the Brauer category. So that actually doesn't contain this proposition in all generality for OSP. It only contains for the orthogonal and symplectic group. But that's actually I think if you want to start, this is the best paper to start with, because there they very explicitly construct this Brauer category. But once you have shown that this functor is actually full, then we immediately get something we already know from Schur-Weil duality. We namely look at the homomorphisms from R to R, then we apply F to it. And if this functor is full, we know that this is surjective. But we know that homomorphism of R to R, this is just a Brauer algebra. So we know that we have a map from the Brauer algebra to this two representations of OSP-V, and it is actually, since we have mapped our generating object to V, R will be mapped to the R tensor product of V. So this shows that this map is actually surjective, which is an important proposition of invariant theory. So we know that this is surjective. We also want to know when this is an isomorphism, and for that we should actually look at the description of this kernel of this map. And that's so-called second fundamental theorem of invariant theory. And if we understand this kernel, then we can use this to see when this map we had before is actually an isomorphism. For example, if you look at this paper by Coulombier, there are earlier papers where the second fundamental theorem of invariant theory was already studied for special cases, so orthogonal cases, symplectic case. Then this allows us to get information on this kernel. So we can show this is generated by a single element. So, but what the surprising thing about this is that we have here a functor which we can study using kind of categorical language, but that we get very concrete results on representations. So this diagrammatic approach and then going to this Brauer category and the linear category allows us to use abstract abstract informations or to study this functor abstractly to really get very concrete information on our representations of the orthogonal groups. And this can actually, I've done all this talk on orthogonal group or the orthosymplectic group, but this actually has also been done for the general linear group. We can also do this in the paraplectic case, and also in that case we get first and second fundamental theorems of invariant theory. So I hope that I've convinced you with this talk that diagrams can actually indeed be very useful to study concrete problem and representation theory. So thank you for your attention.
Okay. Thank you for your interesting talk. Are there any questions? Comments? Remarks? There is a question from the chat. Could you apply the last theorem for Brauer algebras?
I don't really get the question since it is for Brauer algebra. So what we have here is the linear category is actually it was this Carubian envelope of the Brauer category. So in particular, if we look at homomorphisms from R to R, then this is actually the Brauer algebra from, so this, so the Brauer algebra is the homomorphism from R to R. So this functor F gives us a map from the Brauer algebra. So that's what we notice here with phi of R, gives us a map from the Brauer algebra to the endomorphisms of this R-fold tensor product of V, and the morphisms which are in this category, so which are OSP invariant. So in this theorem then gives a description of this kernel, this gives a description of the kernel of this map.
Okay, so Florin Nikita replied, thank you. Okay. Any other questions?
I have a question.
Please, Emanuela.
Yeah, thanks for the talk. I wanted to ask, one of the relations that you showed at some point a few slides back really looked like the Kaufman smoothing relation used for the Jones polynomial up to some signs. You had z minus z instead of z to the minus 1, let's say.
So do you mean
and
this?
Yeah, exactly, precisely. And I was wondering here, I mean, it's not exactly Kaufman, but sort of a skein relation, it looks like. Can you use known skein relations from knot theory to answer this question? Because you were asking here what sort of relations make sense here to generate interesting stuff, and in your quest, have you come across the known skein relations from knot theory?
I haven't looked specifically at that question, but it's indeed interesting that you could ask what kind of relations you get here, and there are certainly links with these Tangle. So also this actually comes originally from, I think, was inspired by this Tangle theory and these relations. But I think indeed it would be interesting to see if we get this skein relation, but I don't know by heart exactly which relations we obtain.
Right. Yeah, okay, I was just wondering. Another question I have very briefly is that these cup and caps, I can think of them as, I mean, other than, of course, there is a dual object and, you know, that's the kind of standard, but I could think of them, for instance, I think in Hopf algebras, it happens with the integrals and co-integrals, right? You can do a multiplication, then a sort of projection of the so think of the cup like I multiply two elements and then I project onto the ground field, which for you would be the unit object. Something like that. So this suggests that, let's say I don't project on the unit object of your category. Can I think of some variation of the BMW category where I have just multiplications and that's it? So I pass from two strings to one string, similar to braided algebras, for instance. Is there anything like that, or is an object that hasn't been studied?
So do you mean that you kind of would have such a relation?
Right, this would be a cumulative. I don't know if you're reading from top to bottom.
I normally read from bottom to top. Yeah.
Okay, yeah. So this would be a multiplication. And of course, vice versa would be a co-multiplication, something like that.
Yeah, I don't think in this setting I don't really have seen it before. But in the beginning, I mentioned the circle by modules. And there they actually do kind of do these things. So I think the setting would be to look there, because there you can do a lot with these diagrams that you indeed can study them. But here, for this orthogonal thing, it's really like in the orthogonal group, you have this bilinear form that you, I don't know if I can do it.
Right, yeah.
It's just a bilinear form, and then just the basis, the dual basis that you actually get here, then you kind of
right is the canonical pairing or the co-pairing.
Indeed.
I was just wondering because I've come across cases where instead of having pairing and co-pairing, you need multiplication and a co-multiplication. I was wondering if this is interesting object of study.
Yeah, I think this circle by module is really where they kind of do, in this book on circle by module, they really kind of do this stuff where this can actually indeed interpret it as a co-multiplication and multiplication, and you have Frobenius algebras and stuff like that.
Right, yeah, exactly. For instance, the delta here would become the handle of the Frobenius algebra, so similar to, okay. Thank you so much. Thanks a lot.
Okay, further questions? Okay, if not, let's thank the speaker again. And we will resume next Monday at the usual time. Bye, everybody.